this again. But I went to college during a time period where they honestly didn't care if they failed the entire class, you know what I mean? So you kind of had to be on top of things because they don't care. Now it's like, oh. Okay, now the area problem. Let's actually work on it. I don't know if you guys heard, but the other day Google's AI failed a math test. Did you guys hear about that? Okay. It was in my newsfeed on my phone. So they pretty much, developed this AI. It's supposed to be awesome, the cutting edge of artificial intelligence, and they gave it I don't remember what grade it was. Maybe a 10th grade math test. Yeah. Is it smarter than a 10th grader? Turns out it wasn't. It failed the math test because it turns out that there are a lot of things that, and this is a part of the problem. A lot of people think, math people make things more complicated than they have to be. No, in truth, there are a lot of things that you do as a human being that seem simple, but it's very hard to articulate it. And actually, when it comes down to abstractions, to talk about it as a list of instructions that something that's not a human needs to follow and be able to do, it's kind of hard. So we spoke about the area problem and how the idea was very simple. You just dissect this thing into a bunch of shapes that you're familiar with, and just have someone add up the areas. Now, if you have a human being actually doing this, not a big problem. If you want to get a computer to do this, or you want to make it abstract and get a nice formal solution to this, that's a different story altogether, right? What does it mean to draw a horizontal line? What does it mean to draw a vertical line? What does it mean to add up the areas? That's kind of sketchy. So first of all, the way we solve the area problem is not going to be this complicated, because this is actually way too complicated for me to tell you how to do something like this. When you get to Calculus 3, you're going to have to do something like that. But until then, there's the erasers over here. Until then, figuring out how to draw both vertical lines and horizontal lines, kind of too complicated. So we want to simplify the situation. Let's just worry about dicing this thing into vertical segments, right? Because this was too complicated. This one, too complicated. Okay, so let's just look at this as, and you'll see why this is complicated. In Calculus 3, you're going to do something like this, and it's going to require something called a double integral with a double summation to actually abstract this. So for now, we're in single variable calculus. We're not as sophisticated as doing that yet. So instead, we're going to count strips. And we're going to want to use what we know about functions. And so, obviously, if I put this on the xy plane, I don't have a function, because functions pass the vertical line test. So that's already another issue. So this is still too complicated. So what we decide to do is, let's just focus on finding half of the object that we care about. So now we can look at it as a function. And now we can talk about these strips. And because those strips are, again, still kind of complicated, because the top parts of the strips are very irregularly shaped, that's where we came up with the idea of, let these strips touch the curve, and we'll use those to define heights of rectangles. And the rectangles are simpler to deal with. And so then we finally came up to this idea, which I introduced at the end of last class, which is the idea of using rectangles to approximate the area under a curve. And ultimately, the goal is to be able to build up to find something like this, but this is where it starts. This is where you really want to break down the process to be as simple as possible, but not too simple, simple enough to deal with the problem at hand, but not so complicated that you won't be able to write down a nice mathematical theory that will describe it. So ultimately, we're going to reduce this problem to figuring out that problem. You want to find how much space some irregular shaped thing takes up? Figuring out how 1/2 of it takes up at a time is how you're going to do it. And instead of doing horizontal and vertical strips, let's just do vertical ones and create rectangles. So that's the idea. So this brings us to what we call a Riemann sum, the process of summing up the areas of these rectangles with the specific purpose of approximating the area under some irregularly shaped curve. Okay? So the area problem, we've reduced the problem to finding the area under curves. And we begin by approximation. Beginning with approximating this area. With rectangles. Now, there are many flavors of how you can do this. We have many ways to do this. Here are some popular ones. So that's the idea. You want to attack the area problem, figure out how much space this takes up, reduce it to a much simpler problem that we can solve with single variable calculus. Well, at the time we didn't know we could solve with single variable calculus, but we're going to figure that out on this journey. So this is the idea that we have to find the area under something. And so there are some popular ways to do this. There's what we called right-hand endpoints. It's a very popular flavor. So here, say you have some function f of x, just doing this thing. You again want to find the area on some interval under that curve. What you can do is you can dissect that interval into several parts. And the right-hand endpoints means for each of these little mini intervals called subintervals, we're going to let the right side of that interval be the part that touches the curve and then slices across. So for this interval, the right side touches the curve, comes across. 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 And so we can construct rectangles with this way. Height of rectangle determined by the right side of the, it's called a subinterval. Okay, so we have the interval that we care about. We slice it up. Each of the mini intervals, we call them a subinterval. So we slice up the interval into subintervals, right? And on each subinterval, we allow the right side to be the guy that determines the height of the rectangle. Whenever we do that process, this is called using right-hand endpoints. Now, what you can notice here is in this case, we have an overestimate of the area. You'll notice that the rectangles cover the area that we care about, but they even cover more than that. And I'm talking about in this case specifically. In this case, my function is increasing, so the right side will always be larger than the left side. So for that, it will give us an overestimate. If our function was decreasing, the right hand would give us an underestimate. But in this case, we get an overestimate because we cover the area that we want, but we cover more than the area that we want. So the area that we really care about is strictly below the curvy lines, the curvy line, and the rectangles give us more than that. So this is called an overestimate. Okay. So that's one way in which we can construct these rectangles. Another way is, of course, the left-hand endpoint. So we can talk about letting the left side of the subintervals touch the curve, and that would determine the height of the rectangle. So we can talk about left-hand endpoints. How about that? And so, give you a very similar looking curve here. So that's our curve of x. So here's our interval. We slice that up into little mini subintervals. And so this time, we let the left side of the curve touch the interval. Touch the curve and cuts across. Left side touches, cuts across. Left side touches, cuts across. Left side touches, cuts across. And we can construct rectangles that way. Because again, you want to give instructions clear enough for a computer to be able to follow it, right? So this is how you're going to tell it to do the rectangles. Go to the left side and plug in that point into the function. That's the height of your function. And so this is what you get here. And in this case, so here, the left side of your solid tool determines the height. And in this case, this particular case in this example, we get an underestimate, meaning we get something that's smaller than the actual area. But it is still an estimation, of course. An approximation. Now, of course, before we got really control of the concept of infinities, this was pretty much the best we could do. You would literally have a human being adding up these areas. Now, of course, the more rectangles they use, the more of these pockets they would fill in, and they'd get a better estimate. Okay, but of course, here it's kind of, you don't want to end up in a situation where you're really fighting against a losing game. You're fighting a losing battle. So you can come up with there's another popular way that tries to minimize the over approximation and under approximation with certain curves, so that you don't need as many rectangles to get to a fairly accurate answer. And this was called the midpoint rule. So this is when you let the midpoint determine the height. Now, what you'll notice from a rule like this is that, okay, I cut it into those 4 sections as always, but now I do something slightly different. I let the middle of the interval determine the height of the rectangle. So I can go in the middle of the first one, that's the height. Middle of the second one, that's the height. Middle of the third one, that's the height. Middle of the fourth one, that's the height. Now, the height is going to be, of course, determined by that. So it would look like this, and this one would look like that, this one would look like that, this one would look like that. Now, what you'll notice with these guys is, on one side they give you an underestimate, but they'll kind of compensate for that by giving you an overestimate on the other side, right? So you have all sorts of rules like this. They're really trying to figure out what is the best way to construct a rectangle for the thing that we're looking at. And sometimes some things are obviously going to give you less than the answer, some are going to give you more than the answer, but some kind of auto-compensate, right? And when you get to Calculus 2, you're going to learn even more sophisticated ways to construct rectangles. You're even going to be able to construct trapezoids like in the trapezoid rule, or parabolic arcs like in Simpson's rule, things of that sort, where now you're beyond just thinking about rectangles. You can think of a little bit more complicated of a shape. But yeah, you have many flavors that you can construct rectangles under a curve. In Calculus 1, these are the main 3 that we expect you to know about. Left, right, left, and middle. And this one, it's kind of hard to say if it's an overestimate or an underestimate because it compensates for itself. And so you're not really sure, is the underestimates the ones that are worse or the overestimates the ones that are worse? But for a lot of things, you would need less rectangles to get more of an accurate answer with this guy than the other guys. And there are some times where one might be better than the other. So it depends on your function. But in terms of paradigms, these are the three main ones we need to know for calculus. So there are going to be cases where I'm going to ask you to approximate an area with a finite number of rectangles, and in the problem I'm going to specifically say, I want you to use the left-hand endpoint, or I want you to use the midpoint, or I want you to use the right-hand endpoint. Right? So I'm going to tell you which one you should be doing, and you should understand the main difference between the three is just how you determine the height. So if the height is determined by the left, that's the left hand. Determined by the right, it's the right hand. Determined by the middle, is the midpoint. That's where they're different. Now, in some sense, they are the same, in which I'm going to show now. So let's actually make this formal, right? So this is an informal introduction. Let's actually write stuff down, make it exact. Or exact as it could be. We're still doing approximations. So we're going to use notations. So here's the interval that we care about, A, B. Okay? So there's a curve on the interval. And so we can dissect it, and we'll always dissect it into intervals, subintervals of equal width. We'll always dissect, just to make things simple, into subintervals of equal width. Namely, delta x is what we'll call this width. This will usually be some section of the x-axis, and so we'll talk about the distance of each subinterval is just the length delta x, change in x. We'll also start to label the tick marks. And so the first guy, we'll normally call it, say, x sub 0. This will be x sub 1, x sub 2, dot, 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 all the way up to x sub n. Okay? So we can talk about having n subintervals, or n rectangles. I should have probably also mentioned that. Number of subintervals. It's not exactly the same, but it's equivalent to the number of rectangles. And we refer to this number is referred to as n. So we want to cut it into n subintervals, n rectangles. So a problem might say, okay, use 4 rectangles to approximate this area. It might also say, use 4 subintervals to approximate this area. It might also say, use n equals 4 to approximate this area. Those 3 statements are all saying exactly the same thing. Okay, so it's just how we're going to talk about it. So delta x is defined like that. Now, your delta x, because it's measuring the subintervals of equal width, and we know we want to slice it into n pieces, what is an equation that would define the delta x? If I want to take the length of the interval AB and slice it up into n equal pieces, what would be the length of each piece? I can actually find a formula for this. What is the length of this interval? Imagine this is a piece of the x. What will be the length of this? I define the length of any horizontal distance.
You can just do delta x times n.
Sure, but
Or b minus a, whatever.
b minus a, right? The length of any horizontal distance is going to be the right minus the left. Right? That's where, when we're constructing the equation of a line, the y2 minus y1 over x minus x1. Same thing. So the horizontal distance is b minus a. I want to divide that into n equals pieces. That gives us an equation that defines this delta x. That will always be our delta x. That's going to be important. That's going to be both for the finite case and the infinite case, which we're going to be covering. Now, let's talk about the actual x values. So, now what I'm going to tell you here, this you need to know. But what I'm going to tell you here is more useful for the next iteration that I'm going to show you, the infinite case. But I might as well just introduce the formula now since we're here. But in the finite case where you only have 4 things, you're going to be able to figure out what the x values are. It's not going to be a big deal. Because to get from this x value to that one, you just add delta x, right? And then to get from this to that one, you add delta x. This to that, and you keep adding delta x to find the new x values, right? How can you write that down in a statement, right? So you realize that, okay, your x naught is going to be a. Your first x coordinate is going to, be, of course, be a plus delta x. And your second x coordinate is going to be the last one plus delta x. But if you plug in the last one into here, you'll realize that that's going to look like a plus 2 delta x. And then you're going to keep x3. Well, by a similar reason, it's going to be a plus 3 delta x, and so on and so forth. So you can talk about, in general, your x values are given by xi is equal to a plus I delta x. So that's going to be a formula by which we can find the x values. Now, it's not going to be super important here, but when we get to the infinite case, knowing how to find the x values is going to be very important. But that's basically it. Now, of course, the height of the rectangle well, that's going to be f of xi, right? Where this guy is chosen according to some paradigm. So it's either going to be right, left, or mid rule. Right, so the guys that get plugged into your function will depend on if you're looking at the right or left or whatever. So notice that if you're looking at the right-hand endpoints, all x values will be plugged in except the very first one. Because the x1 will get plugged in because he's on the right, the x2 will get plugged in, and so on and so forth. The x0 will not be plugged in because he's the guy that's on the left. Versus if you're looking at the left-hand endpoints, the xn is the only one that's going to be emitted. Everyone else is going to get plugged in. If you're looking at midpoints, then all the middles are going to be plugged in. Of course, you can find the middle of something by just finding the average of these two numbers. Add these two, and then divide by 2. That will tell you what's in the middle. And then from that middle point, you just keep adding the delta x again to get all the other middle points. Okay, so with that being said, I think I already told you all the things we need. Well, I did actually write down what I just said formally, so let me just do that. Now, it's going to be clearer once we actually start doing it. when you, to write things down, it actually makes it look a lot more complicated than it is, because it's kind of hard to actually write something down that you can do pretty easily. But formally, we can say the following. I can describe the right hand with the following procedure. Okay? So I'm assuming I'm finding the area under a curve. So area under f of x on AB, where the A is the x0 and the B is the xn. The right-hand rule can be summarized as the following procedure. Pretty much, I'm going to take all the right-hand points and plug into the function. So that's going to look like f of x1 plus f of x2 plus f of xn, and I'm going to multiply these all by delta x. And this will give me an approximation for the area, which we would call r sub n. Okay? And that's an approximation for the area. So I'm plugging in the 1, 2, 3, because x0 is left out because he's on the left side. And I can simplify this by the summation. I goes from 1 up to n of f of xi delta x. This is called a Riemann sum. It has n terms in it, and this is really just an approximation for the area. Okay? So you can think of the right-hand rule as just you doing this, plugging this formula. This guy's b minus a over n, and this guy's the convenient x points that you're plugging into the function. Of course, we can look at the left-hand rule, called L sub n. This is just an approximation for the area using left-hand endpoints. Here we're going to plug in the x0, the x1, plus dot dot dot. We will stop at the xn minus 1 term, because that's going to be the last left point. Multiply all of those by delta x. You can write this as the summation of I goes from 0 up to n minus 1 of f of xi delta x. That's also an approximation for the area according to the left side. And you can also do, so pretty much when I ask you to actually use one of these rules, you're going to end up plugging into this formula. That's to summarize everything. And of course, if you're looking at the midpoint, this is going to look like m sub n. That's going to mean you're going to think of f of x1 star. That's just a notation that we use for the middle. x2 star f of xn star times delta x. That's going to look like the summation I goes from 1 up to n of f of xi star delta x, where, as I said, the xi star is just the average of the two guys on the outer edges. So it's xi minus 1 plus xi divided by 2. So you can copy that down, and we will do an example right now. See this in action. So when it comes to testing you on this, here's what a problem would look like. Now, of course, I'll only ask you to do one of these, but it'll essentially look like this. A approximate the area under y equals 6x minus x squared, or can you put f of x equals that? For x equals 0 to x equals 6, using 3 subintervals. And remember, I could say equivalently, I could say 3 rectangles, or I could say n equals 3, or something like that. And A, right-hand incomes. B, left-hand incomes. C, midpoints. So an example wouldn't ask you to do all 3. You're expected to know all 3, but an example is going to ask you to do one of them. Right? So in a test or a quiz, I'll say, approximate the area under this, on this interval, using this many subintervals and the left-hand rule. And that'll be the end of the problem. But I want you to see the difference between all 3. So we're going to do a slightly larger example than you'd be expected to do. But I can randomly pick any one of these 3 paradigms to ask you about, and you should know how to deal with them separately. So let's look at all of them. You can copy that down. So now we're going to do right hand. So here's how we're going to do it. First, we're human beings, so not computers. So I think setting it up with a picture is going to be nice. Okay, so you're going to put 0 to 6, cut it into 3 equal pieces, and you're going to try to figure out what does each number have to be. Now, you can automatically say delta x is going to be 6 minus 0 over 3, because that's b minus a over n. Which is 2, which means each jump is a jump by 2 units. So this would be 0, that would be 2, that would be 4, and then the last jump of 2 would give me 6. So that's my interval. Now I know, because I'm doing the right hand, I only care about the numbers that are on the right side of any given interval. So the 2, the 4, the 6 are the numbers that I care about, because I'm doing the right hand rule. And so the area is approximately going to be R3, because I'm only using 3 subintervals. And that's going to be equal to, well, f of 2 plus f of 4 plus f of 6, all of that times my delta x. So that is going to be f of 2. I'm going to just go here, I'm going to plug in 2. So it'll be 6 times 2 minus 2 squared plus 6 times 4 minus 4 squared plus 6 times 6 minus 6 squared times 2, which is the delta x. And blah, we're going to figure that out. Like on a quiz and a test, at this point I'll allow you guys to use calculators again. The last few quizzes I didn't allow it, but for this one I'll allow it, right? So you'll do that, then you'll compute the answer. And if applicable, write as a fraction. If applicable. But that's essentially the process. So you know you have to use right-hand endpoints. Just draw a diagram of what the interval looks like, slice it up, fill in the numbers according to what the delta x say you should fill them in with, and then circle all the guys that are on the right. So on the 0 to 2 subinterval, 2 is on the right. On the 2 to 4, 4 is on the right. On the 4 to 6, 6 is on the right. So these numbers get chosen, the guys on the right side. And you would get a number here, and that would be an approximation for the area. Won't be the exact area, because 3 rectangles is nothing, but it's an approximation. So in a test, I'll ask you with 3 or 4. I wouldn't go beyond 4. Any questions on this process? You might have been confused with before, but the example, like it's a lot easier, I think, when you just get down to the nitty-gritty. Thank you. But going over that theory is important for some of the things I'll be able to explain, as well as for many people being able to write something down abstractly is actually pretty important. Let's look at B. B, I would do the same idea. Here's the interval, 0 to 6. I know I want to slice up in 3 pieces. What should be the length of those pieces? Well, my delta x is b minus a over n to 6 minus 0 over 3. That's 2. So again, each jump should be a jump by 2. Now, because I'm using left-hand endpoints, I will always pick the number that's on the left. So on the 0 to 2, 0 is on the left. On the 2 to 4, 2 is on the left. On the 4 to 6, 4 is on the left. I will select these 3 numbers. And so I will now say the area is approximately equal to L sub 3. But that just means I'm plugging in 0, then 2, then 4 into the function, and I'm multiplying by delta x. Because that gives me the height times width, height times width, height times width. It gives me the height times width of all the rectangles. So that would just be 6 times 0 minus 0 squared plus 6 times 2 minus 2 squared plus 6 times 4 minus 4 squared times 2. And that will be whatever. Now in C, you'll do the midpoint. Starts out the same way. 0 to 6, slices into 3 equal pieces. I will go, my delta x is b minus a over n, 6 minus 0 over 3, which is 2. So I know this is 2, this is 4. But again, in the midpoint, that's not the number I care about. I actually care about the numbers in the middle of those guys. And so I can find the first one, x1 star, by averaging these two. 2 plus 0 over 2, it's 1. And so I know the first number I care about is 1. And then from that, I keep adding the delta x. 1 plus 2 will give me 3. 3 plus 2 will give me 5. So 1, 3, and 5 are the numbers that I care about in this iteration. So this will mean the area is approximately equal to the midpoint rule for 3 subintervals, which is simply going to be f of 1 plus f of 3 plus f of 5 times delta x. So it's going to be 6 times 1 minus 1 squared plus 6 times 3 minus 3 squared plus 6 times 5 minus 5 squared. All that times 2, which is going to be blah. Now, clearly all of these three will give you different numbers because we're plugging in different numbers into the function. But there are different kinds of approximations. Some might be underestimates, some might be overestimates. But they'll give you different ways of doing the function. And one way might be better than another way for the kind of function you're looking at. So if your function is strictly increasing or strictly decreasing, probably the midpoint is the best one to use. If your function is doing like a hill like that, then you might use either the left or the right. You might do something different. You can even mix and match. So you can do like the left-hand rule for one half and the right-hand rule for the other one. But we'll keep it simple in Calc 1. Just do one kind of mechanism for a problem. So I'll either ask you to do a right hand in which what I wrote in A will be your solution, or I'll ask you to do a left hand in which what I write in B will be your solution, or I might ask you to do midpoints in which what I wrote in C would be your solution. Any questions on this stuff? So once you do your little chart, figure out the numbers you care about. The rest of it is pretty okay, I think. Okay. Now we move on to phase 2. Sometimes an approximation isn't good enough. Finding the exact area is a lot more difficult for a random curve. The idea is, so we can have this guy slice things into 3, and then do this, 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 or we could take the same guy and instead slice it into 6. And it should start to become clearer what the benefits of this are. See, the more rectangles you use, the less errors you will have. Right? Idea is, the more rectangles, the better. So now you start thinking like a mathematician. Well, what's the best? What's the more that I can do that no one can come up with a better, oh, let's do more than that? Infinity. So this obviously extrapolates to the fact that an infinite number of rectangles is the gold standard. In fact, that gives us the exact area, because you can keep filling it in with so many rectangles. And if you're ever concerned that you're missing anything, just throw in more rectangles. Or we're still missing some, throw in more rectangles. Eventually you'll get to a point where, you know, there's no discernible space that we can see here. We pretty much got it. So that's the idea. Pretty much take what we've done with the right-hand rule or the left-hand rule or the midpoint rule. It doesn't matter what the starting point is. Just let n go off to infinity, and that will cause us to fill in all the gaps. And so the idea for the exact area is to use an infinite number of rectangles. Now formally, what does it mean to use an infinite number of anything? Infinity is not a number we can plug in. However, we developed a mathematical object called a limit, and this allows us to, well, it's the next best thing to plugging in infinity is to just use a limit approaching infinity. And so we can achieve this scenario, and I mean, quite literally, you won't see any spaces. You can achieve that scenario using a limit. And so the idea is to find the exact area. You let n go to infinity, the number of, and so you can also think of this equivalently. Some formulations will talk about delta x going to 0, like the space of the subintervals will just get smaller and smaller and smaller. But I'll do the iteration where we go let the number of rectangles go up to infinity. Okay. Now when you look at it that way, the formal way really becomes important, because it's not like you're going to write down f of this plus f of that plus f of, there's no way to actually express this idea in the Mickey Mouse way that we're doing the other ones, right? Here you have to be a little bit more sophisticated, a little bit more formulaic and strategic. And so basically what we're going to do is we're going to want to set up the formulas. So we know we can approximate the area using what we call a Riemann sum. So this is pretty much the area is going to be approximately equal to the sum. I can do it, say I equals 1 up to n, which reminds you of the right-hand rule way of dealing with things, but it actually doesn't matter which rule we start with. Let's just start with this one for simplicity. Of f of xi times delta x. Now what does it mean to actually compute this sum? Like how can I put that in a nicely written formula? And so this will basically imply that my a will be exactly equal to the limit as n goes off to infinity of this guy. A shorthand for this, you don't need to know it, but the shorthand for this would just be to, on the summation sign, right, I goes from 1 to infinity, of f of xi delta x, and not writing the limit. But every time someone writes that, in the background, they're thinking of a limit somewhere. But this is how we can express it. Now, remember, you're going to be given an interval, so you're going to know the endpoints. You're going to know a and b and all these numbers. And so you want to specifically be able to plug in the numbers so that you can kind of use this formula as a template. And so the formulas that I derived earlier will actually come in handy here. So, in summary, using earlier formulas, we can say the area is equal to the limit as n approaches infinity of the sum I goes from 1 to n of f of xi. But what would our xi's look like? Well, they would look like a plus I delta x. And what is our delta x? Well, our delta x is going to be b minus a over n. You will literally plug in these numbers and then you will solve that limit. Okay? So you're going to know what the A is, you're going to know what the B is. The N, you don't know. The N is going off to infinity. So N is going to be N. But your variable for the summation is I. And this guy gives us an infinite sum of rectangles. In fact, that is why we call it by a very nice notation. We use S for sum because math people are naming things. But we use an elongated sum. This expression, we can write it as a shorthand. We write it as the sum from A to B of our function with respect to x. And we give this sum a name. We call it the definite integral of f. So here we write that S symbol with numbers on it, and of course you're realizing that that was the same kind of symbol we used for antiderivatives. Yes, that's because we eventually learned that the antiderivative is going to be the shortcut for doing this. So this is how you compute the area under a function. This is like the rudimentary way of doing it. So it's like when I told you about derivatives, we use limit as h approaches 0 of f of x plus h minus f of x over h. That's like this kind. But we learn shortcuts like the power rule and etc. That's this side. And it turns out this side, the antiderivative is going to help us out with it. But we'll see that next time. So for now, we'll stop there. And I'll see you guys on Friday. So the quiz today is on optimization and antiderivatives. So look at the formulas, look up how to do antiderivatives, and look over optimization, and you should be fine.